When we picture the mechanics of the cosmos, we tend to imagine gravity reigning supreme. We think of glowing galaxies, massive superclusters, and the dense matter that pulls it all together. But if you map the universe on a large scale, a different structure emerges. Galaxies are thin, glowing outlines wrapped around immense, pitch-black bubbles. These empty regions account for 80% of the volume of the entire universe. Out on those glowing borders, the cosmic walls, things are chaotic. Galaxies collide, dark matter clumps together, and gas burns. But inside these massive gaps, the environment is isolated, sparse, and deeply quiet. Because matter is largely absent here, gravity loses its grip. These gaps are the domain of a subtle force embedded in space itself, vacuum energy, known as dark energy. Without heavy galaxies to anchor it, dark energy acts as a repulsive force, driving the universe's expansion from within these pockets. To find the source of cosmic expansion, astronomers must look away from the matter being pushed and start studying the empty space doing the pushing. Observing nothingness requires massive datasets. Modern telescope missions conduct sweeping redshift surveys, scanning the sky to measure the exact distance and speed of distant light. By charting the 3D coordinates of millions of galaxies, astronomers trace the boundaries of the voids, mapping the terrain by carving out the negative space. When a photon travels across one of these expanding regions, it loses energy, leaving a measurable cold spot. Because these regions lack the gravitational anchor of heavy matter, they undergo super-Hubble expansion, meaning they expand faster than the average rate of the rest of the universe. As a result, the few small galaxies that form inside these regions are actively evacuated. They flow outward from the center of the darkness, eventually piling up onto the dense, glowing walls of the cosmic web. These voids function as the primary drivers of large-scale evolution, dictating exactly where matter gathers and where it is expelled. These same dynamics govern our own local neighborhood. The Milky Way sits on the edge of the local void, sandwiched between this dark pocket and the dense Virgo cluster. Virgo's gravity pulls us inward, while the rapid expansion of the void delivers a violent push from the opposite direction. This local environment creates a major discrepancy in our math, known as the Hubble tension. When we measure how fast the universe is expanding near us, the rate appears noticeably faster than what global cosmic background measurements predict. If we are living on the edge of a rapidly expanding void, that outward push means the galaxies in our immediate neighborhood are being accelerated away from us. It creates the illusion of a faster expanding universe. Living on the shores of this cosmic desert is warping our local measurements, clouding our understanding of the universe's true expansion rate. As we look further out, the empty spaces get larger. Deep in the constellation Canes Fanaticus sits the giant void, an underdense region measuring an astounding 1.3 billion light-years across. This is a scale comparison chart showing a typical cosmic void, which is already immense, next to the giant void. The giant void completely dwarfs it, reaching a scale that defies our standard logic. According to the Lambda CDM model, the standard rulebook for structure formation, a gap this massive should be statistically impossible. There hasn't been enough time since the Big Bang for gravity to move enough matter to carve out a hole of this magnitude. The existence of these supervoids suggests that dark energy may have behaved differently in the early universe, accelerating the growth of these empty regions long before modern theories predict. As dark energy continues to dominate the vacuum, the future of the cosmos belongs to these empty spaces. Over hundreds of billions of years, these voids will continue to swell. They stretch the walls of superclusters until the gravitational bonds physically snap. Galaxies will drift into total isolation, receding past the observable horizon until their light can no longer reach us. The final state of the universe will be dictated by these gaps, as they steadily dismantle the cosmic web until nothing but silence remains.